Hello and welcome to Natural Language Processing 0 to NLP. This is a practical and coding focused introduction to modern natural language processing. The topic for today is neural networks and deep learning. So today we'll continue looking at the Quora insincere question classification Kaggle competition. So here is an example of a sincere question. What is the function of a plasma cell? This is a great question. This is the kind of question Quora would want to have on their website. And this is an insincere question. Why can't liberals realize that they're stupid? This is clearly more of a statement. This is not a question. So we are going to build a text classification model using deep learning and neural networks. So here on the Kaggle competition page, you can learn more about the competition. Specifically in this data tab, you will find that there are a few files. There is a train.csv file, a test.csv file, and a sample submission CSV file. So we have to download these files and then we have to train a machine learning model, a text classification model using the train.csv file and make predictions on the data in the test.csv file. And finally, we can generate some predictions and put them into the submission CSV format and submit them to Kaggle to see our score on the leaderboard. So we're going to move quickly since we have done this before. I encourage you to check out our previous tutorials. I am going to go over to jovian.ai, and in case you're not logged in already, you can sign in and you can create a free account in case you don't have an account already. Now on my profile, I am going to click on the new button and I'm going to click create a new blank notebook, a new project, a Jupyter notebook into which I'll be typing the code. So let's call this Quora classification deep learning live, and let's create this notebook. So now we've created a Jupyter notebook. This can contain some explanations and this can contain some code, but we need to run this Jupyter notebook in order to write the code and execute it. So I'm going to click run and I'm going to select run on Colab. So we are going to use an online execution platform called Google Colab to run our notebooks. And we also have some other options for platforms where you can execute your code, but Google Colab is going to be convenient for our use case today. All right, so let's just call it, let's just give this a title, Quora insincere question classification. And today we're looking at deep learning and neural networks. So let's write out an outline of what we're going to do today. The first thing we're going to do is download the data from Kaggle. The second thing we'll do is prepare the data for modeling using the TF-IDF technique. Next, we are going to train a deep learning model using the PyTorch library. Okay, so with that outline, let us create a few sections in the code. Let us create a few sections in the notebook. So first I'm creating a section called download data from Kaggle. And let me add a few code cells here. And now I'm creating a section called prepare data for training. And I'm going to create a final section called train deep learning model. All right, so now you can see here we have a nice table of contents, which is a good way for us to navigate our notebook. It's always great to start with an outline. All right, so let's start by downloading the data from Kaggle. So to download the data from Kaggle, we can go back onto the data tab of the competition and make sure that you've gone into rules and accepted the rules. Otherwise, you will not be able to download the data. And there is a command here that we can copy, Kaggle competitions download -c Quora insincere question classification. And this is a shell command. So to run the shell command, we are going to have to use the exclamation point at the beginning. So for example, if I just type the ls command, that is going to run the shell command and that is going to show me the list of files that are available here. Now by default, when you start a Colab notebook, no files are available. So it's probably going to print nothing, or maybe it's going to print the sample data that's available here. Yep. So you can see that there is a folder sample data that we have here in our Colab notebook, and that sample data folder is printed here. Similarly, now we are going to download our dataset. Now to download this dataset from Kaggle, we are going to need a Kaggle API key. So you can get the Kaggle API key from kaggle.com/me/account. So I encourage you to copy this URL. I encourage you to copy this URL and open it in a new tab so that you can download your Kaggle API key. So this is going to open up your account settings in Kaggle if you're logged in. And you can click create new API token, and that's going to download a kaggle.json file. Now this kaggle.json file is required for downloading data from a Kaggle competition to any other place, including Google Colab. So I'm going to upload this file, kaggle.json, from my computer onto Google Colab. Okay, it looks complicated the first time, but it's actually fairly straightforward. You'll just keep this file around whenever you want to download a dataset from Kaggle. Upload it on Google Colab. Then we need to tell Google Colab where this file is. So I'm going to type import OS, and I'm going to type OS. I'm going to create an environment variable. So os.environ Kaggle config dir equals. Let's see what the current working directory is. So the current working directory, I believe, is /content. So I'm just going to put Kaggle config dir is /content. All right. So now we have configured the Kaggle command line tool to read the kaggle.json file from the directory /content. And it is going to use the credentials in the kaggle.json file, which was downloaded from your Kaggle account, to now download the data from the Quora insincere question classification competition. Okay. Now, I don't want to download all the files, so I'm simply going to download the file train.csv first. So I'm just going to put in -f train.csv. And apart from train.csv, I also want to download the file test.csv. And I also want to download the third file sample_submission.csv. So let me download that as well, sample_submission.csv. And that's now going to read my Kaggle API key, and it is going to download all of these files for me. Okay. And once I refresh this over here, you can see that all these files have been downloaded. Let me now create some variable names to store these file names. So let's call it train_fname, and it is simply /train.csv.zip. And then we have test_fname, that is simply /test.csv.zip. And finally, we have the submission file. I'm just going to call it sub_fname, that is /sample_submission.csv.zip. All right. So now we have created these variables. These just contain the paths of the files that we just downloaded. Let's now turn these into pandas data frame. So let's import pandas as PD. Now we're using the pandas library. This is a data analysis library that we normally use. So pd.readcsv is the function that we'll use to read the CSV file. And I'm going to create 3 data frames. The first one I'm going to call raw df, which is going to contain the training data. I'm calling it raw data frame because we are going to do some post processing. Let's create a test df from the test file. So test_fname. And finally, let's create a submission df. So sub_df. df is just short for data frame. pd.readcsv sub_fname. Okay. So now we have downloaded the data, and we have now read it in using the pandas library. And we'll be able to look at a few examples now very soon. So let's check raw df. And you can see that raw df contains 3 columns, a question ID, which is not useful for our purposes for training. It contains a question text, and it contains a target. Now these targets can be 0 or 1, and all this information is described here in the data tab of the competition. You can see that the target is 1 if the question is insincere, otherwise the target is 0. In this case, most of these seem to be 0, but you can always also verify that there are some insincere questions. So if you just check raw df.sample 10, you will see that there are definitely some insincere questions that will come up in these samples. So here you can see that there is some comment about Chinese people, which is clearly more of a comment than a statement. And you can just browse through more samples to get a better sense of the data. So that's the raw data frame. Now in the raw data frame, we have about 1.3 million rows of data and 3 columns. The columns you're interested in is the question text and the target. So using the question text and the target, we want to train a system that can look at new questions and make predictions on whether those questions are sincere or insincere, so that Quora does not have to do a lot of manual moderation. So once we have trained our system, then we have to make predictions on the test data. So you can see that the test data frame from the test.csv file simply contains a bunch of questions. So some of these questions seem sincere, some of these do not seem sincere. So simply contains a bunch of questions, and we have to make predictions on these questions. And we have to then make these predictions, and then we have to create a submission CSV file, which contains 2 things: a question ID, just like we have a question ID here, and a prediction for each row in the test set. You can see that the question IDs on the test DF and the submission DF are exactly the same in the same order. So ideally, we want to make a bunch of predictions. Our sample submission file just contains all zeros, but we have to make a bunch of proper predictions, and we can submit that to Kaggle. So that's something that we're going to attempt to do today. Okay. Now the last thing I'm going to do is just pick a small sample instead of using the entire training set, so that we can run our models quickly. And then I encourage you to just try it with the entire data set later. So I'm going to pick sample size of 100,000. So this is how we can write 100,000 in Python. We don't need this underscore, but it just makes it easy to read, and Python still treats it as a number. And I'm just going to pick raw df.sample and with the sample size of 100,000. Okay, and let's check sample df now. All right, so the sample df now contains 100,000 rows from the training data picked at random. We can also verify that it actually contains a good mix of both sincere and insincere questions. So you can say sample df dot target dot value counts normalize equals true. So we are doing a lot of data analysis here. All of this is something that we cover in our data analysis with Python course and also in our 6-month data science bootcamp. So it looks like 93.8% of the data is sincere questions, and about 6.1% of the data consists of insincere questions. We may have to do something to deal with this class imbalance. Okay, so now we are ready to move on to the second step, and I'm just going to save my work. And whenever I save my work, it's going to go back and update my notebook on Jovian. And it's also going to record versions automatically whenever Google Colab is saving my work. And this notebook is going to be present on your Jovian profile so that you always have it handy in case you need to show someone or just run it on some other platform. So let's now prepare the data for training. Again, we're moving fast because we've done this already. So I encourage you to go back to 0to-nlp.com, the course page, enroll if you haven't enrolled already, and check out the previous lesson. There's an assignment on the TF-IDF as well, where we cover some of the basics, but you can do that after you do this as well. So here we are going to prepare the data for training now. So step 1 in the preparation is to convert text to TF-IDF vectors. TF-IDF stands for term frequency inverse document frequency. So we are going to convert text to TF-IDF vectors. That's number 1. Then we are going to convert the text or the vectors to PyTorch tensors. So we are going to use the PyTorch library for deep learning. And then finally, we are going to create PyTorch data loaders. Okay. So let's get into it. First step is to convert to TF-IDF vectors. So let's do that. So the way we are going to convert our text to TF-IDF vectors is using the TF-IDF vectorizer from scikit-learn. So if you just search TF-IDF vectorizer, that's going to tell you all about where you can get this from and how you can use it. So this is part of the sklearn.featureextraction.text module. So I'm just going to say from sklearn.featureextraction.text import TF-IDF vectorizer, right? And let's create the vectorizer. And while creating the vectorizer, we're going to need to provide a few options. So here's what the vectorizer does. Our objective is to take each question in the data, each question in the data set, and convert it into a vector. Now, one way to do it is by simply doing something called a bag of words, which means we look at all the distinct words in the data set. Basically, we create a vocabulary, maybe of the most common words in the data set. So something like this. These are all the distinct words in the data set. And then each question can be replaced with a vector containing the number of times each of these words occurs. Now that is called a bag of words, and that is done using the count vectorizer. We cover this in the first lesson. But in TF-IDF, instead of just using the count, what we use is the term frequency, which is the count of that word in that sentence, multiplied by the inverse document frequency. So here is the formula for the term frequency multiplied by inverse document frequency. So term frequency is simply how many times a particular word occurs in that question. That's term frequency. And then inverse document frequency is the total number of documents divided by the number of documents containing that particular word and the logarithm of that. Okay. So this accounts for words that occur too frequently in the dataset, and this is slightly better than just doing a bag of words. Okay. So ultimately you still get vectors like this for each of the questions. Each question gets turned into a vector that is of the size of the vocabulary. But instead of just using the counts, we use this term frequency multiplied by inverse document frequency. Okay, so to create this TF-IDF vectorizer, we are going to need a few things. So the first thing we're going to need is a tokenizer. How are we going to split our text, our questions? So these are the questions that we have. How are we going to split these questions into tokens that can then be turned into vocabulary words? So let's use that. Let's use the NLTK library. So I'm going to import NLTK. And then from nltk.tokenize, import word tokenize. So that's one thing that we are going to import. So word tokenize, okay, NLTK. So that's one thing we're going to use. So word tokenize can take a sentence and split it into a bunch of tokens. Let's try to run it. So let's try word tokenize. So here is a sentence with a bunch of punctuations. And before we can tokenize, we need to download the punct module within NLTK. So I'm going to download that. And let's tokenize it once again now. All right, so this is comma something, comma. All of these punctuations also get split into individual tokens. So that's great. Now, apart from the word tokenize function, I'm also going to introduce a stemmer, because some of the words like is, etc. occur in pretty much every question, and they're not very useful from the perspective of sincere insincere detection. So I'm going to also perform some stemming. So for stemming, I am going to use the snowball stemmer. So I'm going to say from nltk.stem import snowball stemmer. And let's create a stemmer here. In the language English. All right, so here's what a stemmer does. What stemmer does is stemmer takes some of the words like gone, go, etc. So here's the word gone, for example, and then here's the word going, and then here's the word go. So all of these words have the same root form, which is go. So stemmer is going to convert all of them into go. So if I say stemmer.stem going, that is going to convert it into go. Stemmer.stem gone. I guess that keeps that as gone. So sometimes it works, sometimes it doesn't do that. But if you have something like butterflies, it's going to convert that into the singular format. It's going to convert that into the singular format like that. like butterfly, and it just has put the I. Even if you have butterfly, it's going to convert that into an I, most likely. So stemmer takes all of these words, which can have many different forms, and reduces them to the root form. So that's the stemmer. And we are going to use a snowball stemmer here. So we have a stemmer in place, and let's create our own tokenize function, which can also perform stemming. So let's define a function tokenize, which takes some text, and then it returns stemmer.stem token for token in text. And of course, we want to tokenize the text, right? So we are going to first tokenize the text, and then we are going to return the token only after stemming it. So let's try it. Let's try tokenize. So something like that. It is going to take all of these tokens, and it is going to break it down into individual words and each of the and punctuations, and each of those words it is going to reduce to the root form. For example, unexpect and butterfly, and similarly also amaze. So now we have a tokenizer. So let's pass that tokenizer. So tokenizer is the tokenize function. So this is telling the TF-IDF vectorizer how to split our text into small tokens. Then we need to provide a list of stop words. So some words like is, and, the, etc. will occur so frequently that they're not going to be very useful for our machine learning model, possibly. So typically in a bag of words model, or a TF-IDF model, we remove stop words. So let's get a bunch of stop words from NLTK. So I believe you can say NLTK, let's search NLTK stop words. Let's see here. So I believe you can just use nltk.corpus stop words. So I'm just going to import from nltk.corpus, import stop words. And let's create a list of stop words in the English language by typing English_stop words equals stop words dot words English. Okay, looks like we're going to download this corpus. So let's do the download here as well. I'm just typing in nltk.download stop words, and that's going to download all the stop words, the list of all the words in English that will automatically get excluded while we are doing the TF-IDF conversion. So let's just print out the list of stop words. So here's the full list of stop words. There's a few more here. You can see these are all the words that will get removed while we are converting our text into vectors. So let's provide the stop words here as well. So stop words equals English_stop words. Perfect. So now we have provided a tokenizer. Now we have provided stop words. Some of these are not very relevant. You can also experiment with the n-gram range. So you can also look at combinations of two words or two tokens at a time instead of just looking at single tokens. I'm going to limit the vocabulary size by passing max features. So I'm going to pass max features equals 1000. All right. So now we have created a TF-IDF vectorizer. So this is going to take our sentences, our questions, and it is going to convert them into vectors, and the vectors are going to be created using the TF-IDF formula. So let's do that. So first let us learn the vocabulary from the dataset. So I'm going to say vectorizer.fit sampledf.question text. So we are going to give it sampledf.question text, and once we give it this, it's going to go through each question. It's going to split each question into the tokens using the tokenizer, using word tokenize. And then it is also going to stem each word. So it's going to reduce, let's say, butterflies to butterfly, unexpectedly to unexpect, amazing to amaze, and so on. So it's going to reduce all words to their root forms. Then it is going to remove all the stop words that we have provided. So all the words included in this list are going to be removed. Then it is going to look at the 1,000 most common words, because we've provided max features equals 1,000. So it's going to look at the 1,000 most common words, and it's going to create a vocabulary out of those 1,000 most common words. So now the vectorizer has been fitted, and you can look at the vocabulary by looking at get feature names out. And maybe let's look at the first 100 words in the vocabulary. So these are the first 100 words in the vocabulary, and the overall length of the vocabulary, if you check it out, is going to be about 1,000. That's something that is something that we have configured. Okay, so now that we have created this vectorizer now knows the vocabulary. We can now encode the data. So we can now transform the questions into vectors, right? So far we have just learned the vocabulary, and we have just decided that the first word in the vocabulary is a exclamation mark, then there's a dollar, then there's a percentage, and so on. Okay, so here's what I'm going to do. Because the outputs are going to be used as inputs to a model, so because the transformed vectors are inputs to a machine learning model, I'm going to say inputs equals vectorizer dot transform, and I'm going to pass it sample df dot question text. Okay, so that's going to transform all the inputs, all the questions that we have into vectors. And similarly, I'm going to do this for the test data as well. So remember that we have a test data frame, which also contains a bunch of questions. So here's our test data frame. So this is our sample data frame. This contains a bunch of questions. And then here is our test data frame. This also contains a bunch of questions. Now I should be transforming the test data frame using the same vocabulary that I've learned from the training data frame. Otherwise, the test and the training will not make sense to each other. Okay, so now the inputs have been transformed. Let us take a look at the shape of these inputs. So inputs.shape. So you can see that the inputs now contain 100,000 vectors, each of length 1,000. Okay, and you can check inputs itself. It's going to be a sparse matrix, so you will not be able to see the actual data. But let's say you checked the first element of inputs. So inputs 0, and you converted that to array. It's going to contain 1,000 numbers, basically a bunch of zeros and ones. Let's maybe just look at, yeah, so you can see it contains a bunch of numbers. Let's maybe just look at the first 200 of these. Or maybe even the first 50. Okay, in any case, you can see here that it contains a bunch of zeros, and in some places it contains non-zero values, which demonstrate that this is the TF-IDF score for that item in the vocabulary. So that means this first input, the first question, contains the vocabulary word which occurs at this position, and the weight of that word in this document, in this question, is 0.09 according to the TF-IDF formula. Okay, so now we have the inputs, and similarly let's create some test inputs as well. So here I'm going to say test inputs equals vectorizer dot transform test df dot question text, and let's check test inputs dot shape. And test inputs has about 300,000 rows of data, so this is going to take some time as well. But once this is done, we'll be able to see that it is also converted into 300,000 or so vectors, each of length 1,000, using the TF-IDF formula, using the vocabulary that we have learned from the training set. So that's something important to keep in mind. Okay, now once this is done, and just to recap, what we've done so far is we've downloaded the data from Kaggle, and then we have prepared the data for training by first converting the data to TF-IDF vectors. So that's what we've done, and let's fix the spelling here. So we've converted the data to TF-IDF vectors, and now once the data is converted into the TF-IDF vectors, we can now start to prepare that data for training. So the next step in preparing the data for training is to split the training and validation set. Okay, let's fix that. So we have 100,000 rows of data in the training set. We're going to take the 100,000 rows of data in the training set, and we are going to convert them into training and test sets, into training and validation sets. About 70% of the data will be used for training and the remaining will be used for validation. So let's do that. The way we'll do that is using train test split from sklearn. So sklearn has this train test split function. So I'm just going to import from sklearn.model selection, import train test split. And you can see here that the test inputs have been modified, and the test inputs now contain 375,000 vectors, each of length 1000. So now we've imported train test split from sklearn.model selection, and now we can create a set of training inputs and training and validation inputs. And we can also create a set of training targets and validation targets. And how do we create them? We say train test split, and then we pass in first the set of inputs. So the inputs have been created here. We have taken the inputs here from vectorizer.transform sampledf.question text. So all the 100,000 questions have been transformed into 100,000 vectors. So let's pass the inputs. What are the targets? Well, the targets are simply sampledf.target, right? So sampledf contains not just question text, but it also contains a bunch of targets, as we can see here. And these are the targets that we want to predict. So our model should be able to take this question, convert that question into a vector, which we've done already, and then predict this target. So we're going to set the targets to sampledf.target. And we are also going to split the targets correspondingly with the inputs. And how are we going to split it? So we can provide a test size equals 0.3. And now you will see that your training inputs will have the shape 70,000. So they'll have 70,000 rows. Each is a vector of size 1000. And the val inputs will have 30,000 rows. Similarly, the train targets are going to have 70,000 rows, and just all of these are basically just a bunch of zeros and ones. And we have val targets equals, and that is going to have 30,000 rows. Okay, so that's great. So now we have split a training and validation set. So now we've taken the text, converted that into TF IDF vectors, and now we have created a training and validation set. The next step is to convert these to PyTorch tensors. Okay, how are we going to convert these to PyTorch tensors now? So we're going to use the PyTorch deep learning library for this, and PyTorch requires data to be in its own format, which is PyTorch tensors. A tensor is simply a vector or a matrix or an n-dimensional array. It's similar to the NumPy n-dimensional array or a pandas data frame, but it's just PyTorch's own version of representing things, because PyTorch can also run on GPUs. So let's do that. Now, the PyTorch library for deep learning can be imported as torch. So we say import torch. And now we can create train tensors. So let's say train input tensors as torch.tensor, train inputs, and similarly val input tensors as torch.tensor, val inputs. And let's try to run that. And it's going to tell us that it can't actually read train inputs directly. So if you look at train inputs, it is a sparse matrix because it has a bunch of zeros. So it is considered a sparse matrix. That's how it is created by TF-IDF vectorizer. We can convert it to a normal NumPy array simply by calling .toArray. So that's one thing we're doing. So let's call .toArray here as well. And one other thing we're going to do is we're also going to convert these to floating point tensors. So normally they are double precision tensors or something like that, but we can just convert them to floating point tensors. So don't worry too much about this. Just know, okay, val input tensors. Yeah, just know that we are just converting this to the data type float within PyTorch. And now we have our tensors. So let's try train input tensors. And train input tensors is simply this tensor, which is basically just a matrix. And if you check its shape, it will have the exact same shape as train inputs, except that now it is in a format that can be read by PyTorch while we are training deep learning models. Similarly, let's check val input tensors.shape. That's fine too. Okay, one other thing we need to do is to convert the train targets. So train target tensors is simply torch.tensor train targets, and val target tensors is simply torch.tensor val targets. Okay, so looks like our train targets is a pandas series. So you can see here that this is a pandas series. In fact, you can also just check the type and it's going to tell you that the type is series, pandas series. What we require is a numpy array. So from a pandas series, you can just call dot values and you can get a numpy array. All right. So there we go. Now we have our train target and validation target tensors also converted. Finally, let me also convert our test inputs into test input tensors, torch.tensor, test inputs.toArray.float. I'm going to convert these into float as well, just to make sure that everything is just in the float format. Otherwise, later we may run into issues. So this is one thing to keep in mind. Whenever you're converting data from NumPy or pandas, just convert it into floats. Okay, looks like we have our train target, val target, and test input. All of it is set. So now we've created PyTorch tensors, but how PyTorch works is in deep learning models, because you're typically working with very large models, you often have to train your models not using the entire data set, but using a batch of the data. So PyTorch requires you to create something called a data loader. So just to give you some intuition about how this works, what we have is a total of about 100,000 rows of data, and each of these 100,000 rows of data is a vector of size 1000, right? That's what we've created. This is our training set. Of course, in the training set, we don't have 100,000, we have a 70,000, and then we have a validation set as well, which is about 30,000. Now, PyTorch cannot process all of these at once. So what we do is, instead of taking all 70,000 rows and trying to train the model with all 70,000 rows, 70K, we split the data into batches, right? So each batch has a certain size. So each batch has a size, let's say 128. We'll just pass 128 rows of data into our model, train the model, improve the model, and then get back the better model, and then continue using the next 128 and the next 128 and so on. Okay. So this batching of the entire data set is done using something called a data loader. So we have to create a PyTorch data loader. All right. So how do we do that? Let's see. So let's create PyTorch data loaders. And by the way, if it is getting a bit confusing at this point, then you probably may need to review some basic deep learning with PyTorch. And that is something that you can do with our course, Deep Learning with PyTorch, 0 to GANs. So just head over to 0togans.com, and here you can just watch the first couple of lessons, and you can get a quick sense of how tensors work, how data loaders work, and how neural networks are created. All right. So in case you need some intuition about neural networks, go check out 0 to GANs. But for now, we are just going to go ahead and create our PyTorch data loaders. Since we want to use deep learning for NLP, so let's go ahead. So from torch.utils.data, I'm going to import two things. I'm going to first import a tensor dataset. and I'm going to import data loader. Okay. So first thing we need to do is we need to create a data set. So data set contains both inputs and targets together, because when we split the data into batches, we want to make sure that inputs and targets are sitting together. So train DS is simply a tensor data set, and I'm going to give it the train input tensors and the train target tensors. Okay. And similarly, I'm going to create a val DS or validation data set that is going to be a tensor data set of val input tensors and val target tensors. And finally, I'm going to create a test data set, and the test data set is going to contain, well, for the test data set, we don't have any targets, because targets are something that we have to make predictions for and submit to Kaggle. So I'm simply going to pass test ds equals tensor data set test input tensors. Okay, so now we have our data sets. So now if I say train ds, and if I just try to pick the first 10 rows of data, you'll see that it returns two things. It returns the inputs, the first 10 rows of input, and it returns the first 10 targets. So these are the targets for the corresponding rows of data. All right, so now we have a data set. Now we're going to create data loaders. So I'm just going to call them train DL is a data loader. And this data loader requires a data set. Now, apart from this data set, you can see here you can provide a batch size. So I'm going to use the batch size of 128, but feel free to experiment with bigger or smaller batch sizes. It's not that important. What's important is that you use batches. You have to create batches of data. And here's one other thing I'm going to do. While I'm training the model, each time I go through the entire training set, I want to first shuffle all the rows so that each time the batches that get created are slightly different. They contain a slightly different set of rows. So I'm just going to pass shuffle equals true. Just for the purpose of training, I'm not going to do this in the validation or the test data loaders. And what else can we configure here? So there are a bunch of other options. And if you want to learn more about how to use these, then you can check out our course, or you can also just search PyTorch data loader, and you will end up at the documentation for torch.utils.data. So here you can just look for data loader, and that is going to contain some information about what data loader does and how it works. And there might also be some examples here. Okay. So coming back, we've created a training data loader. We are now creating a validation data loader, val ds, and once again we're going to use the same batch size. And I don't need to shuffle it because the validation data loader is just used for evaluation, not for training the model. And I'm going to create a test data loader. That is simply data loader test ds batch size equals batch size. Okay. Okay, so now we have these data loaders. So all we've been doing so far is just preparing our data. We spent 45 minutes simply taking our text, converting that text, each of those text into vectors using the TF-IDF technique. Then we have taken those vectors and converted them into tensors, PyTorch tensors, which is basically the same thing, just PyTorch's internal representation. Then we've taken those tensors and created these data sets, which is simply a combination of the input tensors and output tensors. Then we've taken those data sets and put those into data loaders, which can allow us to extract batches of data for the purpose of training a neural network. All right. And how do you use batches? You simply say for batch in train DL. So that's batch. And then the inputs here are going to be, so each batch is going to contain two things, the inputs and the targets, at least in the case of training and validation. So I'm just, so from the inputs, the first element in the batch is going to be the inputs, and then the targets. Let me just call it batch inputs so that we are not polluting our global namespace, and batch targets. So the second element in the batch that we get from training data loader in a for loop is going to be the targets. So batch 1, that is going to be targets. And let's just print for now. Inputs.shape is simply batch inputs.shape, and print batch targets dot shape is simply batch targets dot shape. All right. And the for loop will keep giving us batches of data till all the batches from the training data are exhausted. So I'm just going to add a break statement here because I just want to get this information for the first batch. So I'm getting a batch of data from the training data loader. This batch contains two things. It contains a bunch of inputs. It contains a bunch of targets. Now the inputs have the shape 128, 1000. So what we've done now is instead of taking all 70,000 rows of data, we've just taken 128 rows of data. And we have the 128 inputs, which is the input TF, IDF vectors, and we have the 128 targets, which is what we want to predict whether these questions, the questions that are represented by these 1000 vectors, are sincere or insincere. Okay. You can also actually print out the input and targets to see what they look like. And of course, if you don't have this break statement, then it's going to go ahead and print that out a whole bunch of times. How many times? You can actually check how many batches there are in the data loader by just running len train dl, and that's going to tell you that there are 547 batches. And you can verify that 547 batches multiplied by 128 rows in each batch, that roughly gives you about 70,000 rows of data. The last batch has a little less than 128 rows of data, but that's basically how it is. Okay, so now we have taken our data and we have split it into batches. Now we can start building our deep learning model. Okay, so how exactly does a deep learning model work? Well, a deep learning model works, just to give you an intuition, something like this. So let's take just one TF IDF vector. So here I have a question. Let's say, what is the meaning of life? All right, that is the question that has been asked on Quora. Probably a sincere question. Excuse my bad handwriting. We have turned that question into a vector, a TF IDF vector of length 1000. Okay, each of the numbers here represents a particular word in the vocabulary, the TF IDF score of that word in the existing in the sentence that we're concerned with. Okay, so each of these terms here represents one word in the vocabulary. Now, what we do in logistic regression is something like this. We apply a weight. So let's call this W0. Let's call this W1. Let's call this W2. So we multiply each of these numbers by a weight, W0, W1, W2, all the way up to W1000. And then we add up all of this, right? So we just do W1 X1, which is this value, plus W2 X2, plus so on, plus W1000 X1000. We add up all of these and we get the total. And then we take that total, and on that total, we apply the sigmoid function. Okay. So I'll let you review this when you just look back at how logistic regression works. But basically what we do is we apply this function, which takes any set of values and reduces them into the 0 to 1 range. Okay. The sigmoid function takes any value. So any output that you get by performing this W1 X1 business, and we convert that into a value, which is by applying the sigmoid function, which gives us a value between 0 to 1. All right. So what we end up getting is, by passing this one data point into a logistic regression model, we end up getting a value between 0 to 1, which we treat as the predicted probability of the logistic regression model. Now, what is the meaning of life? This also has an actual target. So let's say the target here is 0 because it's a sincere question. And let's say after multiplying these weights, the output that we get is 0.3. So the expected target is 0, but the output that we're getting is 0.3. So what we do is we calculate a loss. So for loss, we use a loss function. So we use some loss function. It is called cross entropy. The details are not important here, but we take the loss and we take the prediction that we get from our model. we take the actual target, and this gives us a loss. Okay, so this is the loss for one element, and similarly we try coming up with the losses for all the different rows of data. So now this is just one row of data for which we have the loss. So for each of these rows of data, so we have a bunch of rows of data, let's say about 1,000. For each of these rows, we pass them through the logistic regression model. We get some output, we get a loss. So we get loss 1, loss 2, loss 3 for all the 100,000 rows. And then we add up all the losses and we basically average the losses. Okay, and this is the overall loss of the model. So how machine learning works is you take the input data, you pass the input data into the model comes up with some predictions, and those predictions are predictions predictions between 0 to 1. These are probabilities in the case of logistic regression. So you take the predicted output and you take the target from the original data and you compute a loss. In the case of logistic regression, it's something called a binary cross entropy loss. So the loss simply tells you how good or bad the predictions of the model are. And then you apply an optimization technique. Specifically, the technique that is applied in logistic regression is called gradient descent. You apply an optimization technique, and through that optimization technique, you change the weights of the model. So remember here, we have all these weights that were multiplied initially with our input vectors. So you change the weights of the model so that the next time you take a row of input data and multiply it with a bunch of weights, the output that you get from the model is slightly closer to 0. Okay, and this is done using a technique called gradient descent. All of this is covered in a lot of depth in our machine learning or deep learning courses. You can watch either one. But the whole point being, send some input into a model, get some outputs from the model, take those outputs and compare them with the targets using a loss function, then pass that loss function, use an optimization method and change the weights of the model slightly so that the next time you pass the inputs, you get a slightly lower loss function. So ultimately, machine learning is an optimization problem where we are trying to optimize the loss of data, which is basically the difference between the predicted outputs and the target outputs, by making some internal changes within the model. Now, what happens with logistic regression is that in logistic regression, you take your entire input. Let's put it that way. So in logistic regression, you take your entire input and you multiply all those inputs with a bunch of weights, and then you add up those weights and you get a single number out, and you use that for prediction. A neural network is a natural extension of a logistic regression model. So what you do here is you have an input. So this is one input, one row of input. Instead of having just one logistic regression model, you take a bunch of logistic regression models. And then you take these inputs and you pass these inputs into this first model. So there are a bunch of weights in this first model. There are a bunch of weights in the second model. There are a bunch of weights in the third model. There are a bunch of weights in this fourth model. There are a bunch of weights in the fifth model, and so on. So you multiply the input with weights, you add up those numbers and you apply the sigmoid function and you get a bunch of outputs here. And now you add another layer of training using these outputs. So let's say here we had 1, 2, 3, 4, 5, 6. Now this time we might try to just do 4 outputs. So now you take the outputs that have been obtained by each of these nodes and pass them once again using a bunch of weights into this. So you get another output here, and then into this and get another output here, into this and get another output here. So essentially we're doing, instead of directly going from one input to a single output, what we do is we go from one input, which is one set of numbers, to an intermediate output. And then we take that intermediate output and then we use that to convert another layer of output. And then we use that to create another layer of output. And finally, we just get a single output. Okay. So, and what we do is we also add some non-linearity. So add a sigmoid function between each of these layers. So essentially what all of this is doing is it is doing a bunch of matrix multiplications. The way this actually works out is you take this data, multiply it with a matrix, and that gives you a bunch of outputs. Then you take that and multiply with the matrix, gives you a bunch of outputs. In between, you apply a non-linear activation function or something, which is sigmoid or ReLU or something like that. So it's doing a bunch of matrix multiplication followed by non-linearity followed by matrix multiplication, and it's giving us a single output. Why do we do all of this business instead of just creating a single node and getting the data out? This is because in a single node, if the input that you're passing contains 1,000 values, which means your vectors are of size 1,000, then in total, the number of weights in your model that you have is 1,000. So you have to learn the relationship between the inputs and the outputs and the targets using just 1,000 weights. That is a bit restrictive. What you can do here instead is that each of these nodes is going to have 1,000 weights. So there's 1,000 weights here, there's 1,000 weights here, there's 1,000 weights here, 1,000 weights here, 1,000 weights. So a bunch of 1,000 weights. So if you, in your intermediate layer, if you have 100 outputs in the intermediate layer, each of those 100 outputs will require 1,000 weights. So you have 100,000 weights in just this layer. And then you can go deeper and you can create more layers as well. So what this allows you to do is two things. One, you have more weights. And when you have more weights, then your model can learn more information. Instead of just 1,000 parameters, it now has probably 1,000,000 parameters, and all of those parameters can learn something unique about your problem. And the second, your model can learn non-linear relationships. Because you have these multiple layers, because you have layer after layer after layer, instead of just directly learning a linear relationship between the input and the target, the model can learn several layers of non-linear relationships, because between these layers you have the non-linearity. Okay, so that's a quick 5-minute introduction to deep learning for you. But what we are going to do now is we are going to create a bunch of these layers, and then we're going to pass our data through these layers, and then finally we're going to get a loss, and then we're going to train our model. Okay. Do check out our deep learning course. We spend a lot of time discussing this in a lot of detail, and you'll work this out carefully. But I'm going to go ahead and start implementing our deep learning model now. Okay, so let's create a deep learning model, and a deep learning model is created using the NN module from PyTorch. So I'm going to import torch.nn as NN, and I'm going to import torch.nn.functional as F. Okay. So the way you create a deep learning model in PyTorch is by creating a new class. So let's call this the CoraNet, and this is going to extend nn.module. And in this, you need to define two functions. One is the init function, which is where you set up the layers of the model. And then, so let me just put in pass right now. And then one is the forward function, which takes a set of inputs, a batch of inputs specifically, and it has to return a batch of outputs. Okay. So first we're going to create a set of layers in our model. So I'm going to create a bunch of layers by putting them inside self. So self.layer1 is nn.linear. So we start out with 1,000 inputs. Remember that each vector or each question has been turned into a TF-IDF vector of length 1,000. So we start out with 1,000 inputs, and I'm going to reduce those to 512. So that's layer 1. Then self.layer2 is nn.linear. Now we are left with 512. And we're going to go from 512 to 256, and self.layer3. And feel free to experiment here with fewer layers, or with maybe even with fewer outputs per layer. And then finally, there's going to be a final fourth layer, which is going to take the 128 outputs from the previous layer and simply return a single one output, which is the prediction of the model. Okay. So what we have done here is we have created a multi-layer neural network. So we're going to start out with 1,000 outputs. We're going to start out with 1,000 inputs. Then we're going to put it into this layer. And from the first layer, we are going to get back 512 outputs. And we are going to put all of them into the second layer. And from that second layer, we're going to get 256 outputs. From there, we're going to get 128 outputs. And from there, we're going to get a single output. Okay. So this is your deep neural network. It has 4 layers, and in each layer, it has a certain set of outputs. So that's the layers. We have set up the layers of our model. The next thing for us to do is to actually define what happens when input is passed through the model. So let's say out equals, first we take the inputs. So the inputs will be a batch of data. So let's say 128 by 1000 or 128 by 1000. And we pass these inputs into layer 1. So we say self.layer1 and we simply pass these inputs into the layer and it's going to give us the output. So self.layer1 inputs, and that's going to give us the outputs. Then after each layer, we need to apply a non-linearity. And the non-linearity that we're going to apply is something called the ReLU non-linearity or ReLU activation. This is simply an activation that is used commonly in deep learning. So f.ReLU out. So we're going to take the output and then pass it through the ReLU function. And then we're going to pass it through the second layer. So I'm just storing the intermediate output back into the same variable, but you can also just say out1 and you can say out2 here. But it's just easy for me to just say out everywhere. But you get the sense what I'm doing. We are passing inputs through this. The output of that we are passing through the ReLU activation function. Then we have layer 2 and then we have f.ReLU out. Then we have layer 3. And okay, not inputs, this should be out. So we take the intermediate output and then pass it through the layer 3, f.ReLU out. Then we have layer 4, finally, self.layer4 out. And then we finally return out. So we generally don't apply activation to the final layer because that is something that will get applied while we are computing the loss anyway. So here's what we're doing, right? We are taking the input, a batch of inputs, and each input is passed through the layer. And then we apply an activation function here to introduce some non-linearity. Then again, we pass data through the next layer, apply an activation, pass data through the next layer, apply an activation. So this is layer 1, this is layer 2, this is layer 3, and this is the input that is passed in. So and finally we have a layer 4 as well, I believe. Layer 1, 2, 3, 4. So 512, 256, 128, and then this is the layer 4, which simply returns output 1. Okay, so that is our neural network. Now let us create this CoraNet. So let's instantiate it. So let's say model equals CoraNet. And now we have a model. And looks like it, okay, we have to pass self here and we also have to pass self here. So this is just how you define classes in Python. You have to always pass self as the first argument. Okay, so now we've created model. So CoraNet is a model that has been created. How can let's see. I believe you also have to do something like this. Let's see here. Yeah, I believe what you have to do is just pass this one other thing, super.__init. I think that is something that is necessary to make this work properly. Again, this is just how PyTorch works. Something that you can look up easily. It's not very important from the purpose of our learning. Okay, so now we've created a model. It contains 4 layers and it can take a batch of data. So let's get a batch of data once again. So let's say let's get for batch in train.dl. And then from the batch, we can get a bunch of, let me just call it batch inputs and batch targets, or bin and bi and bt, batch inputs and batch targets equals batch. And let's just print out the shapes. So let's print inputs.shape, that is simply bi.shape. And let's print targets.shape, that is simply bt.shape. And let's just look at one batch of data here. Okay, so we have 128 vectors in a batch. Remember, we have defined our batches here. So we have 128 vectors in a batch, each of length 1000. So 128 vectors, and for each of those vectors, we also have a target. Now let's pass those batch through the model. So let's pass from the model, let's pass in BI. So each vector is of size 1000, and all of the vectors are going to be passed through the first layer over here, and it's going to become vectors of size 512. All of those vectors are going to be passed through the second layer, become 256, third layer become 128, and we have the ReLU activation applied. And finally, at the very end, we are going to just get out one number for each vector. So batch output is model BI, and let's just print bo.shape, and maybe let's also just print bo itself. BO is simply the batch output from the model. Yep, okay, this is probably too big, but let's just print that. Okay, bo.shape. All right, so we have about 128 inputs that were passed into the model and 128 targets, and the model doesn't look at the targets. The model just takes a bunch of inputs and it returns the outputs. So here we have 128 outputs. Okay, now it is in this format where it is two-dimensional. That is just how neural networks work, but we can always just pull out and get this in one dimension. So now that we have, let's look at a few elements from the batch outputs. So let's look at the first 10 elements. So here are the first 10 elements. You can see that each of these, and let's compare these with the actual targets. So BT, and let's look at the first 10 elements in the targets. So this, and let's also maybe look at BI, the first 10 elements, although they will be too large, but still. So here is what has happened. We have this tensor, this vector of size 1000, the first row of data that was passed into the model, and that returned this output 0.0096 over here after going through the 4 layers. What we are actually looking for is 0.0. So the value it should predict should be 0, right? And similarly for this also it predicted 0.0107. The value we're looking for is 0. So we can actually check how many of these are correct. But for that, we'll have to first do a couple of things. First, we have to convert the outputs into probabilities. Okay, so first what we need to do is convert outputs to probabilities. Because the outputs that we've received, they can be in any range, but we want to first convert them to probabilities. And the way we do that is using torch.sigmoid. Remember, that's what we do in logistic regression as well. We say torch.sigmoid and we pass in the outputs, and that gives us the probabilities. So, and then we can just print probs, maybe the first 10 values from probs. So these are 10 probabilities that we get from our outputs. Our outputs themselves, if we look at the values, some may be negative, some may be positive, some may be larger than 1, but now we've converted them into probabilities. Then we can actually take the outputs from the model and convert it, the probabilities that have been received from the outputs from the model, and then we can convert probabilities to predictions. And here's how we can do it. We say that wherever the probability is greater than 0.5, then the prediction is 1. Okay, and otherwise the prediction is 0. So there's a quick way to do this. If we just say probs greater than 0.5 and then we simply print probs, then we simply print preds, we'll see what that shows. Yeah, so you can see that all of these are greater than 0.5, so that's why it's printing true everywhere. Some of these could be less than 0.5 as well. But if we just do .int here, that is automatically going to convert all the trues to ones, and it's going to convert all the falses to zeros. Okay, so that's one thing that we're doing here. We are converting all of these. First, we're converting all the outputs into probabilities using the sigmoid function. The sigmoid is going to squish them between 0 to 1. And then we are going to convert the probabilities into predictions, which are going to be 0 or 1 specifically, by checking whether the probability is greater than 0.5. Okay, again, all of this is standard deep learning stuff. That's what we do in every deep learning model. Now that we have a bunch of predictions, I'm going to do one other thing. I'm going to remove this additional bracket that we have. And the way I'm going to do that is I'm going to say that while I'm getting the probabilities, I will also just pick all the rows, but from each row, I'm just going to pick the 0th elements, and that's going to just get rid of this one bracket for us. So let's see. Yeah. So now you can see that the first 10 probabilities predicted by the model are these. And the first 10 tensors, the predictions from the model are these 1, 1, 1, 1, 1. And I can compare them to the first 10 targets. So print targets, that is simply batch targets 10. Okay, so this is what our model has predicted all once, and this is what our model needed to predict, which is 0, 1, 0, 0, 0. Of course, we've just created our model. We have not trained our model yet. We've just created our model, so it has not learned anything. It is simply predicting randomly using the random weights that it has. But we can measure the accuracy of the model using a metrics like accuracy or F1 score. So I'm going to import a bunch of those metrics. So from sklearn.metrics, import accuracy score and F1 score. Now, F1 score is a combination of the precision and recall. It's a way to evaluate classification models when there is a high class imbalance like we have in this case, because accuracy is not very meaningful, because if you always predict a question is sincere, you would be 94% accurate because 94% of the data in the training set is sincere questions and only 6% are insincere. That's where this competition, if you check its evaluation section, uses the F1 score, which is a combination of precision and recall, instead of accuracy. So let's just check these metrics. So we can print first the accuracy of the predictions as the accuracy score of, so we need to give the accuracy the targets, which is simply BT, and the predictions, which is simply preds. And we can also print the F1 score, which is the F1 score of the targets and the predictions. Okay. So now you can see that the accuracy of our predictions is 0.01 and the F1 score is 0.03. So that makes sense because 94% of the data, the targets are about 0 and we are almost always predicting 1. So our accuracy is low, that makes sense. And the second thing is the F1 score, that is also very low. That also makes sense. The model has not been trained yet. So what have we done here? We've taken a batch of training data, just 128 tensors. We have passed them through the model after getting the inputs and the targets out of the batch. Then after getting the values out of the model, we've converted them into probabilities using these probabilities using torch.sigmoid. Then we've converted those probabilities into actual predictions. Basically, wherever the probability was greater than 0.5, we've converted the prediction to 1. Otherwise, the prediction is 0.5. Prediction is 0. And then we are comparing these predictions with the targets. So our predictions were all 1s mostly, but the targets were all 0 mostly. And these are not all, these are just the first 10. So there may be some 1s and 0s that are mismatching. And then finally, we checked the accuracy of the predictions with the targets. So what percentage did we get right? Not a lot. And we also checked the F1 score of the targets with the predictions. And that is also something that was pretty bad. Finally, the last thing that I'm going to tell you is the loss. So in problems like these, where you are classifying text into two classes, sincere or insincere, good or bad or whatever, this is called binary classification. And the loss function that is used in deep learning for binary classification is something called the cross entropy loss. So you can say, you can use the torch.nn.functional. So this class, which also contains ReLU and a bunch of other activation functions, you can check binary cross entropy here. And what this expects is this expects a bunch of targets and a bunch of inputs. The inputs being the predictions from the model. So we need to give it the predictions. So I'm going to give it the prediction spreads and I'm going to give it the targets. And the targets is simply BT. And it's going to compute the binary cross entropy loss. Okay, and this expects the predictions to not be int but float. So I'm just going to make them float here. Yep. And you can see here that the loss is 94.53. So the entire point of deep learning or machine learning in general is to compute this loss and then apply some optimization to the model to reduce the loss. Okay. And then the next time the input is passed or the next batch of input is passed through the model, and that is again used to compute the loss, and then again some optimization is applied and the model keeps getting better and better with every batch of training. All right. So now we know how batches work. Now we have set up our deep learning model. So let's now define a couple of functions. First, I'm going to define a function called evaluate, which takes a model and which takes a data loader and evaluates this model's performance on the data loader that was given. So that's one that's one function that we're going to define, evaluate model performance. Then the second function that we're going to define is a function called fit. So fit is actually the function that is going to train the model. So it's going to train the model batch by batch. Okay, so def fit model, and it's going to take a bunch of other things actually, but for now let's just put it like that. We're going to define the fit function. So we need a way to evaluate how good our model is doing right now, and we need a way to then train the model, and that's where we're going to use the fit function. So here's what we'll do in the evaluate function. We're going to first loop over batches. So I'm just going to say for batch in DL. Then we're going to get inputs and targets from the batch. So inputs and targets equals batch. So batch 0 is inputs, batch 1 is targets. We're just getting the tuple out. Then we are going to pass the inputs through the, so let's just also just write it, get inputs and targets. Then we're going to pass inputs through model. So we're going to get a bunch of outputs from the model. So outputs equals model inputs. Okay. Then we are going to convert to probabilities, and probs is simply torch.sigmoid outputs. Then we are going to compute loss. So loss is simply, let's see, loss is simply f dot binary cross entropy of probabilities and targets. That is going to give us the loss. Then we are going to compute predictions. So preds is simply probs greater than 0.5 dot int. And finally, we are going to compute accuracy and F1 score. So all of this we've already done with a single batch. Now we're going to do it for the entire data loader, given any data loader. So accuracy and F1 score. So we have the ACC accuracy, that is accuracy score. And here we need to provide first the targets. So these are the targets, and then the predictions. So remember, loss is computed on the probabilities because we can actually mildly affect the probabilities and still get a better model. But so loss is used for training the model. It needs to be continuous and differentiable, whereas accuracy and F1 score are more for human interpretation. So F1 is simply F1 underscore score of the targets and predictions. All right. Now we want to get the overall score for the entire model. So that's where we're going to just store a bunch of losses, accuracies, and F1s in these lists. All right. And what I'm going to do is simply say losses.append loss.item. So that's just going to get from the PyTorch tensor the single value out. And then I'm going to do F1. Then I'm going to do accs.append acc. Well, I believe it's, let's see, we'll print it out and then we'll see what happens. And then I'm going to do f1s.append F1. Yeah, just F1. So for now, let's just do that. And let's just see what that gives us. Okay. And finally, we are going to simply return the average loss across all batches. So I'm just going to say torch.mean losses and torch.mean accuracies and torch.mean F1s. And I believe because these are lists, I will have to convert them into tensors. So I'm just going to say torch.tensor here, just to convert this into a tensor. Okay, so that's our evaluate function. I hope it's clear what it's doing. If not, just take a batch of data and work through this line by line. But let's say evaluate model and let's give it train DL. So what we're going to do is go through a bunch of, okay, torch.nl. I believe it's entropy. Let's fix that. So now we're training using a target size that is different from the input size. Okay, where are we getting this error? Yeah, I think we may just have to, when we're getting these outputs from target, we want to get rid of that extra dimension. So that's where I'm just going to put in the 0. Yeah, so the model is now taking in the data. So it's going to take in all the batches of training data. For each batch, it is going to generate outputs, convert those to probabilities, compute the loss, convert probabilities to predictions, and compute the accuracy and F1 score. And then it's going to print out all this information. So 0.6974, 0.61, and 1.1143. Let's just put these on separate lines just so that it's easy to see. And I'm finally also just going to get the actual item out of all of these, just to make it a bit easier to read. Okay, so we have losses, accuracies, and F1 scores. So the average loss for the model currently on the training set is 0.69. The average accuracy of the model is 6%. Maybe it's always predicting 1. And the average and the F1 score for the model is 0.11. Okay, that's on the training set. And let's also evaluate the model on the validation set, on the validation data loader. So on the validation data loader, it is also again has a loss of 0.69, has an accuracy of 6.1, and has a F1 score of 0.11. So the model is pretty bad right now. It's low in accuracy, low in F1 score. It has a high loss. All of these are high. So now we're going to train the model. So how do we train the model? Remember, we have to take the loss and then use the loss to perform some kind of optimization. And then that optimization technique that we use in this case is called gradient descent, and that is going to then improve the model slightly. So here's what we're going to pass it. So when we train the model in epochs, which means we pass the entire data set through the model many, many times. So we're going to decide how many times we are going to train the model. So we're going to pass a bunch of epochs. And then we're also going to use something called a learning rate. So gradient descent, the optimization algorithm has a learning rate. Then we are going to pass the model, and then we're going to pass the training data loader. We're going to pass the validation data loader. And I believe that should be sufficient for us to train the model. So to train the model, the first thing we need is to create an optimizer. So I'm going to create an optimizer OPT from nn dot. Okay, I think I can just use torch.optim. And there are many optimizers available. So this optimization method that you can use, there are many of these available. I'm going to use the Adam method, which works quite well. And so you can see torch optim Adam. This is an optimizer. So this is where you give it the loss, and using the loss, it can actually then train the model slightly. And the optimizer needs to receive the parameters of the model. The optimizer needs to receive a learning rate. And I believe the optimizer also can receive something called a weight decay. So let's see, torch.optim. Let's check the Adam optimizer. So the Adam optimizer can take a bunch of parameters. So these are the parameters of the model, the weights of the model, the learning rate, and then and you can also provide something like weight decay for regularization. Again, more deep learning stuff. So I encourage you to check out the deep learning course, but this is how it works. So torch.optim.atom, and we say model.parameters. Then we pass in the learning rate, and I'm going to just use a weight decay of 1e minus 5. This is simply just to avoid overfitting slightly. And now we can say for epoch in epochs. So one by one, we are going to just, epoch is simply a number. It's simply the number of times we want to pass the entire data through the model. First, we are going to get batches from the training data set. So we say for batch in train DL, we get inputs targets equals batch. And so what we're going to do here step by step is get inputs and targets, then get model outputs. So outputs equals model inputs. Then we're going to compute the loss. So we're going to compute the loss from the model, and the way we compute the loss is we simply say loss equals f dot binary cross entropy. And we are going to give it two things. We are going to give it the outputs of the model. Well, actually we need to give it the probabilities. So get probabilities. So probs is simply f dot or torch dot sigmoid. And here we give it outputs. But remember, there's that extra dimension that we need to get rid of. That's why we have this. So we give it a bunch of outputs, f dot binary cross entropy outputs and probabilities, and that's going to compute for us. We give it the probabilities and we give it the targets, and that's going to compute for us the loss. And now this is where we perform the optimization. Right? So what we do here now to perform the optimization is three things. We say loss.backward. Now this is getting into PyTorch related things. And then we say optimizer.step. And then finally we say optimizer.zeroGrad. Okay. So what is this doing? Well, this is performing the back propagation algorithm to improve the weights of the model using gradient descent. So what happens is, first, when we call loss.backward, it computes the derivative of the loss with respect to each individual weight within the model. Second, when we say optimizer.step, we use that derivative or that gradient of each weight to slightly adjust each weight. And then finally, when we say optimizer.zeroGrad, now that we've updated all the weights, now that the weights are slightly better, we're going to clear out all the gradients or derivatives that were calculated for each weight. Okay. So this is really the optimization part that's happening. That's going to go into the model, and all the layers internally have a bunch of weights, and it's going to improve each weight slightly based on the loss. And next time for the next batch, hopefully the loss will be lower. Okay. And that's basically it. That is the training phase of the model. So this is in each epoch. We are going to take all the batches from the training set, and for each batch, we're going to perform this gradient descent optimization technique. Then we have the evaluation phase, where after each epoch, we also want to just evaluate the model and print the outputs. So we are going to get back from here, we're going to call evaluate for the model on the validation data loader. And what does evaluate return? Evaluate returns three things. It returns the loss, accuracy, and F1 score, the average loss, accuracy, and F1 score for the validation set. So loss, accuracy, F1, right? That's what it returns. One thing I'm going to do is I'm going to actually just keep track of the history, epoch by epoch history of the loss, accuracy, in F1. But let's also print it. So let's print epoch. So this is the epoch number we're going to print here. And in this epoch, the loss is such, and the accuracy is such, and finally the F1 score is such. Okay, and I'm just going to put in here dot format, and we're going to put in epoch +1. Okay, this should be inside the for loop because we're going to evaluate for each epoch. So epoch +1 here to print the epoch number. Then loss that we got back, we're going to print that, and then the accuracy, and then the F1 score. Okay. one other thing here we're going to do is just print 4 decimals. Otherwise, this can get quite large and difficult to read. So this is just some string formatting within Python to just print 4 decimals. All right. So now we are printing this information. And then finally, I'm also going to just do history.append. And I'm going to append into it the loss, accuracy, and F1 score. Okay. I believe that is basically everything we need. I think this is called optimizer. So I'm just going to call it optimizer here. So now we have just implemented the entire training loop for training a deep learning model. Again, a lot more detail in the 0 to GANs course, but now we can call fit, and let's run this for maybe 5 epochs, or let's run this for 10 epochs, no problem. Well, maybe 5, let's do 5. And let's use a small learning rate. So every optimizer requires a learning rate, which decides how fast or how slowly you want to make changes to the weights. So I'm just going to use the learning rate of 0.001 for Adam. That's the recommended learning rate. The way with learning rates is you experiment with 10 times more or 10 times less. And if your model is bouncing around a lot, your loss is not decreasing, then you can reduce the learning rate. And then let's pass in the model. Let's pass in the training data loader. Let's pass in the validation data loader. And now our model should start training. Okay, well, let's see. The Adam optimizer, okay, we are passing in a weight decay. It should just be called WIGHT-DECAY. And this should be a range, so that we go from, let's say we want 10 epochs, then the value epoch goes from 0 to 10. So epoch is simply one iteration or one round of training with the entire data. And now the model is being trained. So this is it. This is our deep learning model that is getting trained right now. And you can already see that we started out with a loss of 0.69 and an accuracy of 0.06 and a F1 score of 0.11. Now our accuracy has already reduced significantly, and our accuracy has now gone up to 0.94 and 0.35 and is the F1 score, and now it's gone up to 0.37. So it's already doing, if you remember, we trained a logistic regression model the last time in our initial tutorial. It's already doing better than the logistic regression model. And as it trains a little more, it's going to get a little better as well. I think one thing also we can do here is we can simply return the history, and we can actually store that history outside if required. Yeah, so our epochs, our loss is down to 0.15. It's still around that number, but our F1 score is actually getting significantly better. Although accuracy is stuck at 94, probably can't beat 94% accuracy as such, but our F1 score is getting better, which means our model is in fact making predictions on data. Let's give it a few more seconds to run the entire training loop. So yeah, it got to about 0.42. And I encourage you to now experiment a little bit with the number of epochs. I encourage you to experiment with the learning rate. And one other thing you can do is in our loss function, we can actually introduce class weight. So I'm going to do that, and I'm going to show you how class weight has an impact. So let's actually check binary cross entropy online. So let's check PyTorch binary cross entropy. Okay, so now binary cross entropy takes an input and takes a target, and it also takes a weight. Now the weight is provided to match, okay, the weight is applied to the class 1. So in this case, the issue is that 94% of the data has the weight 0, and the class 1, 94% of the data has the target 0, and the class 1 is only present in 6% of the data. So while computing the loss, we might want to give a higher weight to the value 1. We want our model to pay more attention to predict the value 1 correctly. Okay, so I'm going to just make that change here right now. I'm going to go into the evaluate function, and I'm going to pass a weight equals torch.tensor. Let's see. So 95% of the data has the class 0. Only 5% of the data has the class 1. but I want to give both of the classes equal importance. So what if for each data point with class 1, I give it a weight of 20? So let me do that. So what that will do is that each will roughly become, the classes 1 and 0 both will roughly become equally important from perspective of the loss. Okay. While computing the loss for the classes, for the observations where the class is 1, it is going to apply this weight of 20. So I'm going to apply this weight of 20 here. I'm going to apply this weight of 20 here, and let me run this once again. So I'm going to evaluate model. Let's get rid of this. Let's get rid of this. I am going to run the fit execution once again. And now let me just recreate the model from scratch. So we have model equals coronet. And let me start with a empty history. So I'm going to also record the history of the model, history of training. And let me first say history equals, or history dot append evaluate model on the validation data loader. So let me first, without training the model, let me just evaluate the model on the validation data loader, just to see what is its base performance without any training. Okay, so now let's check history. And you can see that it contains this base information of the loss is 13.2. That's a very high loss. The accuracy is 93.8. It's probably always predicting 0. And the F1 score is 0, really bad. Now, let us fit the model. So I'm going to call fit. I'm going to call fit with 0.001 once again. And I'm going to pass in the model. I'm going to pass in the training data loader. I'm going to pass in the validation data loader. And again, I'm going to just, now this is going to again return the history, which is itself a list containing all the average values of loss, F1 score, and accuracy for each epoch. So I'm going to just take this list that is returned and add it back into the history that we have, so that later we can plot it and visualize it and things like that. Okay, so now our model is training, and it is going to take some time to train. It's going to take about 5 epochs, about 2 minutes to train. But that's a good opportunity for us to just recap what we have done. We have downloaded the data from Kaggle. Then we have taken each text, each question text, and converted it into a vector of size 1000 using the TF-IDF technique. Then we have split the data into training and validation sets. So we have used 70,000. So we were already working with a sample of 100,000 rows, and we've used 70,000 of those rows for training and 30,000 for validation. Then we've converted that into PyTorch tensors by using torch.tensor. And then we converted it into PyTorch data loaders, because PyTorch requires you to pass the data into a model in batches. Then we defined a deep learning model containing 4 layers. So it is going to take those 1000 elements from each vector, turn them into 512, take those 512, apply a nonlinearity, turn them into 256, turn those 256 into 128, and finally simply return one output. So it was a 4-layer feed-forward neural network, a very simple linear layers in PyTorch. Then we defined an evaluate function to evaluate the performance of the model on the validation set. And the initial performance of the model was pretty bad. 13.2 was the loss, 0.938 was the accuracy. Although this accuracy doesn't mean anything because the data is very skewed. And finally, we are now training the model using the fit function, which basically performs gradient descent, which is for each epoch, we get a batch of training data, we get the inputs and targets, get outputs from the model, then we compute probabilities, and then we compute the binary cross entropy loss using the probabilities and the targets. And we have provided a weight of 20 to the class 1 because it's very rare. And then we perform the back propagation optimization technique using the Adam optimizer. And finally, after each epoch, we also print out information about the loss of the model. So we've been able to get to a F1 score of 0.38. And I believe if we just went a little bit longer, and maybe you can see that the F1 score actually decreased a little bit. So what I'll do is I've just reduced the learning rate a little bit. So this is something that we do. You have to play around with the learning rate to make sure that the model can, if the model is bouncing around too much, reduce the learning rate. If the model is not training fast enough, then increase the learning rate. So something like that. And once this is done, then we can also probably plot the history. So let's take a look at the plotting code as well. So let's say, let's do this. So from the history contains three things. It contains a list of tuples. Each tuple contains three elements. So I can get from the history just the losses as item 1 from item in history. And similarly, I can get all the accuracies as, item 0 losses. Accuracies would be item 1 from item in history. And then I can get all the F1s as item 2 from item in history. And we'll see this in just a second, what that looks like. But once we have that, we can actually plot the losses. So we can say from matplotlib, which is the library for plotting, .pyplot, or import matplotlib .pyplot as plt, and plt.plot losses, and we can just say plt.title loss. So we'll plot that in a second. Let's just wait for this to complete. So once again, this score has still gone down a little bit. Maybe we train for a little longer. Maybe the score might go up once again. So we can experiment a little bit in terms of the model itself. But you can see that this is the history. This is the history of training of the model. And okay, it should say for item in history, not from. Yep. And now let's plot the losses. So you can see that the loss has actually started to go up a little bit. So we may want to maybe play around with the hyperparameters a little bit. Maybe we may want to reduce one of the weights, reduce the weight here or something like that. But the loss has started to go up. Then let's also try accuracies. And the accuracy has gone up and down, but it has stayed between 93 and 94. Let's also try plotting the F1 scores. And the F1 score has come to about 0.4. Yeah, so I believe if you experiment a little bit, you will be able to get the F1 score up to about 0.5 on the validation set. And at that point, you can now actually make predictions on some real data and see some examples, right? So let's try make predictions on example data. So let's get some examples here. So let's get maybe a small df is raw df dot sample of 10 rows. So this is small df specifically. And here we have these questions and here we have the targets. Maybe let's try 20 so that we have at least 2 questions. Yep. Let's pick another sample just so that I'm getting, okay, these are all ones. Yeah, I'm going to just try for a couple of times till I get maybe at least a couple of ones. Okay, this is looking good. So here clearly you can see that there are some decent good questions, sincere questions, and then there are definitely some unsincere questions like that. Now let us convert these into vectors. So let's turn these into small inputs. So the inputs would be, well, actually let's define a function f predict df, which takes a data frame containing question text and target. And let's see, so just takes a set of, takes a data frame containing question text and target. So first we get the inputs. Inputs will be vectorizer. So remember our TF-IDF vectorizer, we can use it to transform df.questionText. So that would give us the inputs. Then we can pass the inputs into the model to get the outputs. That was given the outputs of the model. Then we can get probabilities from the outputs by doing torch.sigmoid. And the probabilities in this case would be outputs. And of course, we have to get rid of that extra dimension. Then finally, we get predictions, which is simply probs greater than 0.5 converted to int. And we can just return the predictions at this point, I believe. Yep. So let's try predict df. And what is it going to do? It is going to take our question text. It's going to take our sampled small df. It's going to turn each of these into vectors. Okay, what's happening here? Oh, we need to turn them into tensors as well. So, and also into a data loader. So I'll do that. So let's do input. Oh, actually, we don't need the data loader. We can just get a bunch of tensors. So input tensors equals torch.tensor inputs.toArray dot float. And we can just pass input tensors. Yep. I encourage you to try this out line by line so that you can actually see it working. But here is the prediction. So let's compare that with the targets. So let's see small df dot targets or target dot values. So here are the targets, here are the predictions, and let's also look at the questions to compare which ones that got wrong. Small df dot question text. In what ways WhatsApp has what, and let's just call dot values on this so we can read the whole thing. In what ways has WhatsApp changed since being acquired by Facebook? That's a fair question. So the target is 0, which is sincere. The prediction is 0, which is sincere. That's correct. This one also seems to be correct. And let's see which one it got wrong. This one, it was actually, why are women so unsexy? That's clearly a statement disguised as a question. So the target is insincere and our model's prediction is insincere. So that's good. I think our model got everything correct. That's very interesting. Our model in this case is 100% accurate. Let's try maybe another sample. Let's see if our model is still going to be correct. So this is very interesting. Just looking at examples and seeing where your model goes wrong. Again, looks like the model got it correct. So there are 10 questions here. And the question here is why are there a few so Americans, etc., willing to call so-and-so person? That's clearly an insincere question, and that is detected by a model as such, right? So remember, what we're doing is we're converting the input into vectors, then into tensors, passing them through the model, getting probabilities and converting those probabilities into predictions. Work it out line by line, step by step. It will make sense. Let's try one more. Let's see if we can get one example at least where the model is doing wrong. Okay. Now we have one example where the target is 1, but the model gets 0. Okay. When will people realize that using the word myself in the context of if you have a problem, you can contact Bill, Mary, or myself is wrong? Okay. So this is a tricky one for sure, right? It seems like a sincere question. It's a long question, but there's nothing here which is very clearly indicative that it is insincere. Although you can see that this is more of a statement, not a sincere question. So in this case, our model was not able to get it right, but clearly it needs to be marked as insincere. So this always helps looking at examples of what the model is doing wrong, because you can then maybe get more data of that type and then maybe play around with those weights of those specific samples in the training set to make the model a little better. Okay, so with that, we have now made predictions on our training set on some example data, and we know how to use the model. Anytime you're given a question, you can actually just take that question and maybe chuck it into this kind of a data frame. So create maybe a data frame containing just one column and one row from that question and test it out, right? So you can also just, instead of saying predict df, you can create a function predict text, something like that. So predict text, and this just takes some text, and your df is then simply going to be pd.dataframe, and you can just say question text is simply that one piece of text. something like that. And let's try predict text. So let's maybe try this. We had a couple of examples here. What is the function of a plasma cell? So what is the function of a plasma cell? Okay, that predicts 0, which is correct. And let's try this. Why can't liberals realize that they're stupid? Clearly a bad question. And it predicts 1. Isn't it almost like magic at this point? All we have done is we've created this machine learning model, which is nothing but a bunch of matrix multiplications with a few non-linearities in between. And then we've optimized it by passing the data multiple times in batches and just changing the weights of the matrices. And now you can give it some text, and that text first gets converted into a bunch of vectors, TF-IDF vectors, and then it is classified as a sincere or an insincere question. So that's great. Now, one last thing we can do is generate predictions for the test set. So let's do that as well. Now, we have the test inputs already. Actually, we have a test DL already. So we have a test data loader already. Remember? So this test data loader has been created from test inputs. We converted test inputs into tensors, and then we created a test data loader. So we can just say for test DL or for batch in test DL. We can, let's see, let me define a function here. So just to make it easier, let me call it make submission, which takes a data loader and it's going to, or make preds, which takes a data loader and comes up with predictions for the entire data loader. So for batch in DL, and then the inputs is simply going to be batch 0. Yep. And then we are going to pass the inputs through the models to get the outputs. Model outputs. And then we're going to get probabilities from the outputs. So we say torch.sigmoid outputs. And we do that trick where we are reducing that inner dimension. Then we get predictions from the probabilities. So that is simply probs greater than 0 dot int. And this is just predictions for one batch, or this is just predictions for one batch of data. So what we can do now is we can say all preds plus equals preds, but preds is a tensor. So I'm just going to convert this to a list. So I'm going to say dot detach dot numpy and then convert that into a list. So this is just the way to convert PyTorch tensors into a plain list, right? And I can quickly show you how that works. So if I just say dot detach, that is going to remove all the PyTorch tracking internally that it does. So it's not something that is visible, it's going to be required. And when I call dot numpy, that is going to now convert that into a numpy array. And then if I call list on this, that is going to convert that into a list. Okay, so that's what we're doing. We're turning the predictions for a batch into a list, and then we are adding it to the all predictions. So that's make preds, and now test preds is simply going to be make preds on our test data loader. Okay, it should be called model inputs. Now it's going to take a while because the test dataset contains 300,000 rows of data. So all of those 300,000 rows of data are, of course, they've already been converted into TF-IDF vectors. So all of those vectors are then going to be picked in batches of 128. And those batches of 128 are going to be passed into the model. From the model, we are going to get back some inputs. we're going to get back the outputs, which are going to get converted into probabilities, which are going to then get converted into predictions. And then we are going to take the predictions across all the batches and add them into test spreads. So you can see here, test spreads. Let's check the len, test spreads. So the length of test spreads is about, okay, I believe I forgot to return this. Well, instead of maybe converting it into a list, we can simply convert it into a NumPy array. And we can just do this, np.array, and it's going to be a bit faster instead of just converting that into a list. Yeah, np.numpy concatenate. Let's just check that. numpy.concatenate and give it a list of arrays, and it's going to join those along the axis 0. So let's just do that. And I'm just going to append all preds.append preds.detach.numpy. So minor optimization, doesn't really matter, but might save us some time. So I'm just doing np.concatenate all preds. What this is going to do is it's going to take the NumPy array returned for each batch, and it's going to join them all together into one large NumPy array. Okay. So advanced NumPy tricks, not really necessary. All we are looking for really is to take all the, oh, forgot to return. So I'm going to stop this once again. Let's run that again. Yeah. So now this is going to take a while, and then we're going to look at the length of test spreads. But this is a good time for us to maybe recap entirely what we have done. So we started by downloading the data from Kaggle. We are looking at the Quora insincere question classification problem. Now we downloaded it using the Kaggle command line tool, for which we had to put our kaggle.json file here into Colab, and we had to configure this environment variable. Once we downloaded it, we were able to load up the training, test, and sample submission CSV files using pandas. You can see that the training set has a question text and a target and a question ID, which we don't need. And similarly, the test set has just questions. It doesn't have any targets. And what we need to do is make predictions for the test set and put them into the submission file in this format. Now, we just picked a sample of 100,000 rows of data, but we could have worked with more. And we saw that about 94% of the data is sincere and about 6% is insincere. There seems to be an error here. Okay, so let's import NumPy. All right, so then once we had downloaded the data and picked a sample, we decided to convert the text into TF-IDF vectors using NLTK and the TF-IDF vectorizer from sklearn. So we created a tokenize function which takes a text, converts it into tokens, and also stems each token using the snowball stemmer from NLTK. Then it is going to create a TF-IDF vectorizer, and then we fit that vectorizer on the question text of the sample data frame. Takes a minute or so, but now it ends up with 1,000 values because we've limited the size of the vectorizer to the vocabulary to 1,000, and we've also removed stop words. We've provided a list of stop words to remove. Then we transform the inputs, so the training data, which is the sample df.question text, into these TF-IDF vectors. Then we transform the test inputs also into TF-IDF vectors using the same vocabulary. So we don't fit the vectorizer again. We use the same vectorizer. And again, all of these get converted into 1,000 vectors of size 1,000. Then we create a split between the training and validation set. So we use 70% as training and 30% as validation. So 70,000 vectors as training, 30,000 as validation. Then we convert those validation and training sets into PyTorch tensors. And then we convert those PyTorch and also the test data. Then we convert those PyTorch tensors first into data sets, which is just putting the input tensors and target tensors together. And finally, data loaders, which can give us batches of data, batches of 128. And we were able to look at some example batches and verify that they had the right sizes. Then we created a deep learning model, a feed-forward neural network using the nn.linear class. So inside the nn.linear class, there are a bunch of weights, specifically 1000 times 512. So 512,000 weights just inside this, and then maybe 1/4 of that here and 1/4 of that here and so on. So the way this neural net works is it takes its inputs, passes them through layer 1. So it gets about 512 outputs. Then applies an activation function, passes it through layer 2, gets 256 outputs. Applies an activation, passes it through layer 3, gets 128 outputs. Passes it through layer 4 and gets 1 output. We created the model, and then we looked at one batch of training data. We got inputs and targets from the batch. We then trained the model. We passed the inputs into the model to get outputs. Then we converted those outputs into probabilities using torch.sigmoid, because logistic regression or any neural network for classification is going to predict probabilities, and the outputs can have an infinite range. So torch.sigmoid reduces them to the 0 to 1 range. Then we converted those probabilities into predictions of the model. If the probability was greater than 0.5, the prediction was 1, otherwise the prediction was 0. Then we checked the accuracy score and the F1 score of the predictions, and both were pretty bad because the model was not trained yet. Then we also computed the loss using f.binary cross entropy. And the loss in this case was about 94, which is pretty high. And the loss requires you to pass in not preds, but probs. So there is an error here. For the loss, we should actually be passing in probs, not preds. So this is an error that we should fix. We should just call this probs. And then now that we saw how to work with one batch of data, we created an evaluate function, which is going to loop over all the batches, compute the loss, accuracy, and F1 score. And it is going to give us the average loss, accuracy, and F1 score of the model for a particular data loader. So we also defined a fit function, which is going to actually train the model. It's going to take a number of epochs, and it is going to loop over the number of epochs. So that is the number of times we want to repeat the training. It's going to get batches from the training data loader. It is going to get inputs and targets. It is going to get outputs from the model. Then it's going to convert those outputs into probabilities. It is then going to compute the loss of the model. It is then going to perform optimization. This is the gradient descent optimization using an optimizer, which has a learning rate that we have configured here. So we are using the Adam optimizer with weight decay. It is then also going to compute once the training is done. So all the batches in the training data loader have been processed and the model has been trained a little bit in that epoch. It's going to compute at the end of the epoch the loss, accuracy, and F1 score on the validation set, and then it is going to print out that information. And it's also going to store it in a list, which will be returned. So we created CoraNet. We checked initially that it had a loss of 13 and accuracy of 0.93 and F1 score of 0. Then we trained the model first for 5 epochs with a learning rate of 0.001, then for 0.0001, and then we got the overall history, and we got the F1 score to about 0.40, 0.43. It can go higher. It can go up to 0.45 if we tried. And we looked at the losses, accuracies, and F1 scores. Then we plotted them. So this is what the loss looked like. Ideally, it should just keep going down. So there is some improvement to be done here in terms of the optimizer, in terms of the learning rate. We can experiment a bit. Then the accuracy also, we saw that it kind of stayed between 93.9 and 94.5. That's fine. Accuracy is meaningless for this particular problem. But the F1 score, we can see that it is consistently on the upward trend, although it is flattening out somewhere around 0.5. Now it's important to also look at predictions on example data. So here we look at some predictions on example data. So we have the small DF, which we created, about 10 samples, contains 9 of these are target 0 and 1 is target 1. We tried multiple samples. We created this predict DF function, always a good idea to create helper functions. Then we looked at the predictions from our model for that sample, and we compared them with the targets for that sample. And we could ultimately find a question where our model was doing wrong, and that can give us some information about what more we need to do. Then we also created a predict text function, which takes a single piece of text and converts that into a data frame and then passes that through a bunch of processing and finally gets a prediction. And we saw that the question that we started out with, what is the function of a plasma cell, was classified as sincere. And the other question we saw, why can't liberals realize that they're stupid? That is clearly an insincere question. That is something that was captured here by the model as well. So we've more or less achieved our initial target. And then we are now generating predictions for the test set. So now we've received some test predictions. If we look at test preds, you can see that we now have these predictions for the test set. And we can now take the test predictions. Looks like the test predictions are always 1. That seems wrong. Let's see, test preds dot value counts. Okay, looks like there's something wrong with the test spreads. We may want to just make sure that everything is done properly here. So we have a batch that we're getting from the data loader. Inputs are simply the batch 0. And then we pass the inputs into the model. And let's look at a sample batch from the test data loader. Batch from batch for batch in test DL. And then let's just break here and let's just print batch 0. Okay, so this looks fine. Maybe let's just print batch 0, 0. Oh, batch 0 is the inputs. So maybe let's print tensor number 0 from the batch. Okay, looks like it has a bunch of non-zero values, so that it is fine. So inputs is simply batch 0. And we pass the inputs into the model and we get a bunch of outputs. And then we call torch.sigmoid to get a bunch of, okay, this needs to be 0.5. So there was a small bug here. That is why we were getting this, always getting the value 1. And there are always bugs in code. And the way you do it is just by trying out small things here and there. And you can fix these bugs. It's no big deal. But you always just have to be careful. You have to be in full control of everything that you've typed, all the code that you've written. And if you do that, you're fine. Now, once this is done, we are going to take the test preds and we are going to put them in as the prediction in our submission data frame. So test preds. And we'll also look at the submission data frame before that. And then we can do submission data frame dot to CSV. Yeah, so now we have a bunch of 1s and 0s. So let's look at the submission data frame. And let's now put in, instead of these predictions, which are there in the sample submission file, let's put in the test preds. And let's do subdf dot value counts for the prediction. And you can see that we'll have a combination of both 1s and 0s and not just a bunch of all 0s. And now we can say subdf.toCSV submission.csv, and we need to pass index equals none. Otherwise, pandas weirdly adds an index column, and that gives us the submission.csv file. The submission.csv file is something that we can submit on Kaggle. So you can go in here and you can go under submissions and you can make a late submission. Now, there is one issue with this particular competition. It's not there with all competitions. In this competition, you're not allowed to upload a submission file. In this competition, you'll actually have to create a notebook on Kaggle itself. So I'll just show you how to do that. So you can just save this notebook, come back here and run this notebook on Kaggle. So you just select run on Kaggle, and that is going to then open up the notebook on Kaggle. Of course, on Kaggle, you need not download the data. You can actually just use the data that is already connected. So you'll have to connect the competition and run it. So all of this is something we did in the first tutorial. So I encourage you to go back and look back at the first tutorial. But if you also go back into the course page and go into neural networks and deep learning, and here you check the notebook that is provided. In this notebook, we have written it in such a way that this notebook is going to work both on Google Colab and on Kaggle. On Google Colab, you'll have to just add the kaggle.json file. On Kaggle, you'll have to connect the notebook with the competition. So I did this. I ran this notebook earlier, and this gave me a score of 0.45. So logistic regression was able to give us a score of about 0.39, and neural networks have been able to grow our score to 0.45. That's a feed-forward neural network. Now remember, I'm still only working with a small fraction of the data. I'm still not really haven't fine-tuned the neural network, haven't applied regularization, dropout, batch normalization, all of that. So you can probably push it to 0.50 with a little bit of effort, and I encourage you to try and experiment with that. But let's see where 0.50 is going to put us on the leaderboard. So a lot of people have gotten 0.70, and we'll see if we can get to 0.70 or not. But 0.50 will put us probably somewhere, I think even maybe we might even be able to get to about 0.53. So it has moved us up significantly. So we are now in, okay, we're still pretty low, and part of it just could be that there are some public kernels which might have a high score which we're not able to use. However, consider that we started out with an F1 score of 0.1 if we just made random predictions. The best F1 score is 0.71, and we've already reached about 0.5, 0.52 if you train on the entire model. 0.52 from 0.7 is far closer than 0.11. So we've already made a lot of progress. And the next time we are going to look at recurrent neural networks, which are going to make this even better. Okay, so that's everything that we have for today. So thank you for joining. This is Natural Language Processing 0 to NLP. All the course material is available at 0to-nlp.com. So do leave a comment or do share this video if you found this useful. Especially with deep learning, it really helps if you work out things line by line and print outputs in your Jupyter notebook. So we are building towards the model in this picture, which is the attention model. So we have maybe a couple more lessons to go there. But if you're following along so far, if you're working through the notebooks yourself, you will be able to get to this quite easily. Thank you and have a good day or good night. Bye.